I am Dr. Saroja, retired professor in chemistry. Today I am going to talk about accuracy, precision and significant figures. Let's begin with uncertainty in a measurement. Analytical chemistry is a quantitative science and there are always measurements and the result is always numeric. These measurements use devices and we need to calibrate the devices to obtain meaningful data. As a result, there is always an error and a deviation from the value which is inherent in the measurement. One of the uses of statistics is to provide an estimate of the likely value of the error. In other words, we have to establish the uncertainty in the measurement. Let's see what is accuracy of a measurement. Accuracy is the closeness of a result to the true value. It is the level of measurement that gives the true value as well as consistent results. It has no systematic or random errors. The observed results are in agreement with the true results. This can be applied to a single measurement or multiple measurements. But more commonly, it is applied to the mean value of several repeated measurements. If the mean value is closer to the true value, it is said to be accurate. For example, true weight of a weighing bottle, let's say, is 10 grams. And a student takes two measurements of the bottle and gets 9.93 grams in the first place and 9.95 grams in the second measurement. The reported values are precise because they are close to each other. But they are not accurate because they are far away from the true value. Now let's see what is precision. Precision is the closeness of two or more quantities to each other. And this is the level of measurement that gives the same result when repeated. It has got repeatability. If you weigh a substance 5 times and you get the same weight, let's say 2.5 grams is the weight of the object. If you get the same weight every time, then your measurement is said to be very precise. Precision is independent of accuracy. There is no connection between the two. Repeatability. Precision is the repeatability, the fluctuation in a measurement taken by a single instrument or by a single person under the same conditions. Reproducibility, whether the entire experiment can be reproduced in its entirety. That is also precision. Now let's compare precision versus accuracy. Precise measurement need not be accurate. It need not be close to the true value. The result may be precise, close to each other for several measurements, but may not be accurate because it's not close to the true value. Similarly, a measurement may be accurate, close to the true value, but not all measurements may be close to each other or precise. The best quality scientific observations are both precise as well as accurate. Let's see this with the help of this wheel. In the center of the bullseye is the true value. And these three red dots, they are close to the true value. These three are three different measurements and these measurements are also close to each other. So these measurements are precise and these measurements are also accurate because they are close to the true value. Let's take the blue dots. These blue dots are close to each other, so they are precise. But at the same time, they are not accurate because they are far away from the true value. So this is the comparison between precision and accuracy. Now let's take another example and compare precision and accuracy. There are 4 wheels. In the first wheel, the measurements, all 4 measurements are far away from each other. They are not precise and they are also not accurate because they are far away from the true value. True value is the center of the bullseye. Let's take the second wheel, B wheel. B, all the measurements are very close to each other. They are precise, but they are far away from the true value, so they are not accurate. Let's take wheel C. In wheel C, the measurements are all dispersed. They are all scattered. But if you take the mean value is close to the bullseye, that is the true value. So it is accurate. But the results are all scattered, therefore it is not precise. Now the last wheel, D. Here the values are all very close to each other, so they are precise and at the same time they are also close to the true value, so they are accurate. So this is the best scientific measurement that one can have. Now let's see what are significant figures. Significant means important. Significant figures are significant or important digits which convey the meaning according to its accuracy. The number of significant figures are the digits known with certainty. The uncertainty is specified by writing uncertain as well as certain digits. For example, 33.4 grams. 33 is certain and 0.4 is the uncertain number in the measurement associated with the number. Number of digits are in a figure that express the precision of a measurement instead of magnitude. All the experimental measurements have some kind of uncertainty associated with them. What are the rules of significant figures? The first rule, all non-zero digits are significant. For example, 1, 2, 3, 4, 5, 6, all non-zero are significant, and here in this measurement there are 6 significant figures. All zeros between non-zero digits are significant. For example, 256.0017, between these two non-zero digits there are 2 zeros. These 2 zeros are significant. So the total number of significant figures in this number is 3 plus 2, 5 plus 2, 7 significant figures. All zeros that are on the right of a decimal or on the left of a non-zero digit are merely placeholders and are never significant. For example, on the right of a decimal, these 2 zeros are not significant. Only 3, 4, 5 are significant. So this figure contains 3 significant figures. Trailing zeros that are on the right of a decimal are significant only if a non-zero digit doesn't follow them. For example, 10.00, after the decimal, these 2 zeros are significant. This figure has 4 significant figures as the value is known up to 1/100th of an mg. If you write 0.00, that means this is known with an accuracy of up to 1/100th of mg. So these 2 zeros have significance. But if it is just written as 10 and suppose you drop the zeros thinking that zeros have no value, but the value that is 10 mg, it means that it is known only up to a precision of 1 mg. That is why these 2 zeros have to be written at the end. All zeros on the right of the decimal after the last non-zero digit after the decimal point are significant. For example, after the decimal, these 2 zeros are not significant, but these zeros after the non-zero digits are significant. Hence, this figure contains 5 significant figures as the zeros after the decimal are not significant. These 2 are not significant, but these 2 are significant. Trailing zeros in a whole number with no decimal shown are not significant. For example, 420 has only 2 significant figures. This 0 is not significant. So these are the rules of significant figures. Now let's see rounding the results. If we use a calculator for any calculation like calculation of molarity in a volumetric analysis, we may get 12-digit answer. Depending on the calculator, we may get a 8-digit answer, 9-digit or 12-digit answer and so on. Although the answer is correct, it is all presumptuous. You start with 2 digits and the answer is 12 digits. No apparatus can give you an accuracy of 12 digits. The result can't be more accurate than the limit of the apparatus used for the measurement. For example, the burette used in the laboratory has a limit of plus or minus 0.1 accuracy. We can read only 0.1 in a burette. Hence, the result can't be more accurate than plus or minus 0.1 and should be rounded to plus or minus 0.1. Similarly, the result of a calculation can't be more accurate than the least number of significant figures in the values used. 4.08 into 10 to the power of 4 has 3 significant figures as 10 and 4 are not significant. So 10 to the power of any power, if you write 10 to the power of anything, that will not be significant. Only the number is significant. So this has got only 3 significant figures. Rounding of significant figures. If the number you are rounding is followed by 6, 7, 8, 9, that is greater than 5, round the number up by 1 digit. If the number is followed by 0, 1, 2, 3, 4, round the number down by 1 digit. When the digit is exactly 5, the number is rounded up by 1. If the previous number is odd, rounded down by 1 if the previous number is even. When more than one digit is left, rounding off should be done as a whole instead of one digit at a time. Rounding of tens, hundreds, thousands. 83 is rounded to 80, this is tens. 86 gets rounded to 90, tens. 781 is rounded to 800 in hundreds. 9876 in thousands is rounded to 10,000. Example, 0.3378 is rounded to, if you are rounding step by step, it will be rounded to 0.338 in the first place because the last digit 8 is greater than 5, so the previous number gets up by 1. And if you want to round it further, this 338 is greater than 5, so the previous number becomes 4, 0.34. And if you want to round it up further to one significant figure, then 4 is less than 5, so this gets dropped and the number becomes 0.3. Another example, 0.3478 is rounded to, the last digit is 8, so the previous digit gets up by 1, 0.348. Then if you want to round it further by another digit, it becomes 8 is greater than 5, so it becomes 35. And this is rounded to 0.4 because 5 is an exactly 5, so the previous number is odd, therefore the previous number goes up by 1. This is one significant figure.
It's 6 o'clock.
Let's see rounding of result in a calculation. The result of a calculation can't be more accurate than the least number of significant figures in the values used. For example, addition subtraction, the answer should have the same number of decimals as in the limiting term. For example, 7.88 plus 16.4 plus 15.495 plus 75.08973, the answer is 114.86473. This should be rounded to one decimal because according to the rule, addition subtraction should have the same number of decimals as the limiting term. What is the limiting term? Here 2 decimals, here 3 decimals, here 5 decimals, and limiting term is only 1 decimal. So the answer must be rounded to 1 decimal, that is 114. If you keep rounding from the right end, 3 is less than 5, so this remains as 7, and this is greater than 5, so this becomes 5, and if this is exactly 5, this is an even number, so it remains the same, and 6 is greater than 5, therefore this becomes 9. So the answer is 114.9. Now when we come to multiplication division, answer should have the same number of significant figures as in the limiting term. What is the limiting term? Here the limiting term is 3 significant figures. Here the limiting term is 2, 4, 6 significant figures. So limiting term is 3 significant figures. If you multiply 2.56 by 35.2514, you get 90.243584. But the limiting term has 3 significant figures, so this should be rounded to 3 significant figures. This 4 last digit gets dropped. This is 8 greater than 5, so this becomes 6. 6 is greater than 5, so this becomes 4. 4 gets dropped, so this becomes 4, and you get this 4 gets dropped and you have only 90.2 ultimately. So 90.2, 3 significant figures, least limiting significant figures is the answer. Thank you. Thank you for a patient hearing. If you like my video, please subscribe, and next video I am going to talk about different kinds of errors. Thank you so much.